This video will cover permanganate oxidations of alkynes. Permanganate oxidations of alkynes will be very similar to the permanganate oxidations of alkenes. As a reminder, when we treat alkenes with permanganate under mildly oxidizing conditions, where the permanganate is dilute and cold, we oxidize just the pi bond to give the diol. If we treat an alkyne with similar conditions, aqueous permanganate, we see oxidation just of the pi bonds to give us 4 alcohol functionalities. This tetrol is very unstable and cannot be isolated. It rapidly loses 2 molecules of water to give the diketone. Treatment of a terminal alkyne under these conditions again produces the tetrol, which rapidly loses 2 molecules of water to give the dicarbonyl. However, the aldehyde proton is rapidly oxidized in these conditions to produce the carboxylic acid. So, just like we saw with permanganate oxidation of alkenes, permanganate oxidizes not only the pi bonds of the carbon-carbon multiple bond, but any hydrogens attached to those carbons as well. Now let's consider what happens when we treat an alkyne with permanganate under harsher, more strongly oxidizing conditions. Again, let's start with a reminder of what happens with the alkene. If we treat this alkene with permanganate that is concentrated in the presence of heat, we get first the diol, but this diol is unstable under these very strong oxidizing conditions, and the sigma bond between the 2 carbons that were once double bonded also cleaves and is oxidized to produce the ketone from the left-hand side of the alkene and the carboxylic acid from the right. If we treat an alkyne with permanganate under more strongly oxidizing conditions and in the presence of base, we go through the dicarbonyl molecule that is the product of permanganate oxidation of an alkyne under milder conditions, but the more strongly oxidizing conditions also cleave the sigma bond between these 2 carbons. This produces the carboxylic acids. Because this is under basic conditions, the carboxylic acids are deprotonated. Addition of acid is necessary to produce the uncharged carboxylic acids. In the case of treatment of a terminal alkyne under these conditions, we first go through the alpha keto carboxylic acid that was the product of treatment of this alkyne under less strongly oxidizing conditions. But just like in the previous example, the strongly oxidizing conditions continue to oxidize this molecule and cleave the sigma bond between these 2 carbons, giving us the carboxylic acids after treatment with acid. The dicarboxylic acid on the right is known as carbonic acid and very rapidly dissociates to give carbon dioxide and water. So the products of treatment of a terminal alkyne under strongly oxidizing conditions is a carboxylic acid, in this case the carboxylic acid shown on the left, as well as carbon dioxide and water.